Okay, so this is the second part of 10.6. We're going to pick up where we left off. We did the first 22 problems with radicals and solving equations in the first part, and the second part will be about triangles and distances. So it's more of a geometric looking viewpoint of looking at how radicals are involved with things like triangles and distances and stuff like that. Okay. So let's first of all talk about triangles because it's a really good spot to shift gears here and talk about something other than, where are we? There we are. Okay, so let's talk about triangles. What kinds of triangles do we have? Well, triangles are all three-sided and are closed. So it's a three-sided closed polygon is the definition of it. And we have different types. We have acute triangles, where all the angles are less than 90. We have obtuse triangles, where one of the angles is bigger than 90. We have isosceles, where two of the sides are the same and two of the base angles are the same. We have equilateral, where all sides are the same and all angles are the same. And then we have a right, where one angle is exactly 90 degrees. Okay, so this is acute. This is obtuse. This is isosceles. I don't know if that's spelled right. Equilateral, lateral, and right. So those are just some types of triangle. Oh, and then we have scalene too. Sorry. Why can't I go over there? No, I can. A scalene triangle is where all sides and all angles are all different. Okay? Nothing's the same. Okay, so we're going to concentrate on the right triangle for this particular section. The right triangle says that one of the angles is a 90, so we put that box in there. Okay? So let's talk about what a right triangle really is. Okay, so we have certain properties about a right triangle. Okay, so we have one angle is a 90, so this is your 90-degree angle. These three angles add to 180 in every and any triangle. All right, so if we know this one here, then we know that one there. The side that sits across from the 90 degrees is the angled side when it sits upright like this, and this is called the hypotenuse. All right, it's the longest side of the three. And it's always across from the 90, so you can always find it. And for right now, until you get into some right angle trig, we're just going to call these legs. So this is a leg and this is a leg, and these legs are interchangeable. It doesn't really matter which is which. Okay? So if we have a right triangle, we're going to designate, instead of all those words on there, we're just going to designate them as A, B, and C. A and B, it doesn't matter where you put them, but C is always the hypotenuse. Okay? And there was a guy named Pythagoras. He was a Greek. And he invented, well, he didn't, but they don't think that he did, but they still named it after him. But he had a formula that related these three sides. And that was that the square of this side, if you take the square of that one and you add it to the square of that one, which is the two legs, add it together, it always equals the square of the third side, the hypotenuse. Okay? I always ask people in my classes, when do you think Pythagoras was around and when did this thing come about? But I usually get answers like 1700, sometimes 1900s. This guy was born, or he was around in 500 BC. Really, really old dude. He was actually a mathematician, and he what they did was when they were building or planting crops, they couldn't get these two to be exactly perpendicular to each other. So they put ropes. They put one here and they put one there, and then they put one there and one there, and they measured them, and then they tweaked it until this side came out just perfect according to this equation. So the people that used the Pythagorean theorem were called rope stretchers, and they used that to get a nice edge on a building or a nice straight crop or whatever they were doing. Okay, so this is called the Pythagorean theorem. Pythagorean theorem. What's a theorem? We haven't talked about that yet, I don't believe. A theory is, okay, I'm going to say that this holds true. I'm just saying it's a theory. That means it's a pretty good shot. It's a guess. It's a, I haven't proven that it's true, but it sure looks like it. That's a theory. Okay, so when something like this is proven to be true for all right triangles, then it becomes a theorem. All right, so this has been proven. I think it's an 80-page document to be true, which I certainly don't want to go into proofs. I hate proofs, but this is true for any triangle that has a right angle in it. Okay, this does not hold true for other angles or triangles, so it doesn't hold true for these. Okay, none of these. It doesn't work. It only works on that one. Okay? So here we have our Pythagorean theorem. Let's first of all see if we can identify whether or not it's a right triangle. Well, if it's a right triangle, then the Pythagorean theorem should hold. So we have a triangle with sides A, B, and C. Okay? And we want to know if it's a right triangle or not. Let's do this one says it's 5, this one says it's 12, and this one says it's 13. Okay, and the question is that a right angle then, if I had these sides? Well, let's plug that in here. Let's do 5 squared plus 12 squared has to equal 13 squared. Okay, that's your A, that's your B, and that's your C. If this comes out to be true, then it is a right triangle. If it's false, then it's not. So we have 5 squared plus 12 squared, that's 169, and then we've got 13 squared on the other side, 169, so this is definitely a right triangle. Okay, it forms a 90-degree angle because of the lengths. The lengths are forcing it to be 90 degrees. This is definitely a right triangle. Well done. So this first part, you're just going to start checking to see if these things are right triangles or not. Doesn't matter what kind of numbers you have. Okay, so we're always going to go with the A, B, and the C. A, B, C. Okay, so we're going to have the square root of 6 squared, that's your A squared, plus the square root of 7 squared, that's your B squared. And that is supposed to equal C squared. Well, we know something about squares of square roots. We just did that for the entire last few problems here. The square root of a square is itself. So this is just 6. The square root of a square is itself, and likewise here. Is 6 and 7 14? Not usually. It's usually 14, isn't it? Or 13. Okay, so this is not a right triangle. If I had a triangle with these sides, it can't form a right angle in there. Okay? It doesn't hold true. This is not a true statement. So you can go through these and, you know, here's another one. I'm not going to do all of these. There's a ton of them in here. Here's another one. All right. Okay, so now what we're going to do is we're going to find the missing side. That's what the Pythagorean theorem does for you. If you have been given any two sides to a right triangle, you can always find the third side through the Pythagorean theorem. Okay? It allows you to find that missing piece. So here we have a triangle that has a right angle in it because it's got that box in it, and it's been tipped. Okay, it's just been rotated around from what we've seen in the past. But all we need is to designate that this is your hypotenuse. This is the hypotenuse because why? It's sitting across from the 90. Okay, this is a leg and this is a leg. This is either A or B and this is either A or B. It doesn't matter which is which. I'll just say this. Okay, so I'm going to take my Pythagorean theorem, which is a squared plus b squared equals c squared, and I'm going to plug in what I know. I know A is 3. I know B is 3. And C is the piece that I'm missing. It's what I'm looking for. All right, so now I'm solving for C. So 3 squared is 9 plus 9 is equal to C squared, right? I've got 18 equals to C squared. Now how do I get rid of a square? Well, I take a square root, right? Both sides. The square root of a square is itself. And I've got the square root of 18. All right, I'm not going to take the positive and negative values on these because I can't have a negative length. So I'm just going to take the positive root. Well, the square root of 18 is not perfect, right? So we're going to have to, and I'll prove it to you here, it's some sort of decimal, and it doesn't want, that's what my answer is for the second part. That's my approximation. But the first part says, give me an exact answer. Well, my exact answer is the square root of 18. It's exactly the square root of 18. But I have to go back into my radical rules and say, well, how do I express radicals? Well, I know that I can't have a perfect square underneath there, right? I have to take it out. So I can say, well, 18 is 9 times 2. And then I can split it. Square root of 9 and the square root of 2. Right? Square root of 9 is 3. Roots of 2 is C. So that'll be your exact length. So you really do need to go back into all of your exponential rules and make sure that these things are expressed. You have to simplify it, and we know the rules of radicals. And now we have the approximation. Okay, it wants it to the nearest thousandth, so that's 3 decimals. Let's see if the square root of 18 is the same as 3 times the square root of 2, which is better be. Otherwise, something's off. See how it's exactly the same? So either you could do the square root of 18 or you can do this one. To the nearest thousandth is this decimal. So we look to the right, that's a 6, so that becomes a 3. So it's 4.243, I believe. Good job. Okay? So that one's pretty simple, straightforward. If we're looking for the hypotenuse, that's on this side. We're going to plug in what we know. We're going to go through and use our radical rules and solve for what that side is. They don't have to be nice whole numbers either. Okay, so let's try it again. We have that flipped triangle still. Just been rotated around. We've got A, B, and C. This time we know A is 12 and we know C is 20. B is what we're supposed to look for. So again, I'm going to take out my Pythagorean theorem. Okay, I'm going to fill in what I know. I know A is 12. I don't know what B is, and I know C is 20. So let's get some numbers on those. 12 squared is 144. And 20 squared is 400. Okay, so what I'm doing over here is I'm squaring 12 and I'm squaring 20. Now I'm solving for B. So I would go up here. I've got 144 plus B squared equals 400. So I'm going to subtract my 144 across. Okay, I'm isolating B. So 400 minus 144 is 256. Now I've got to get rid of my square. How do I do that? By square rooting. I only want my principal value here. Okay, so this is a B. The square root of a square is itself. And let's check to see if the square root of 256 is perfect. I mean, wouldn't that be nice? It is. It's 16. Okay? Answer is, I did the second function square root of second function, the answer. So it takes the answer from the previous line and throws it in there. Sometimes it's a trick that we can do here. All right, should we check that? Fantastic. All right, so I'm going to leave you be. There's a ton of these in here, okay? Nothing's, the only thing that you really have to remember is, like, this one's pretty simple. It's this one that, you know, the radical rules, breaking apart your radicals. Okay, just be careful with that. This one looks just slightly different, maybe. I don't know. I'm not going to do them all, but I should do a fair bit of them just so that we get lots of practice. I don't want you to panic when it comes to this stuff. All right. So just draw your generic triangle. A, B, C, A squared plus B squared equals C squared. We have the square root of 11 squared plus B squared equals C squared, right? Don't worry if it's a square or if it's a whole number or whatever it happens to be, just write it down. So now I know the square root of a square is itself. B squared equals 49. I would subtract 11 across. So we have B squared equals, what, 38? What's in a 38? What are my perfect squares? 1, 4, 9, 16, 25, 36. I don't think anything's in there. Is 16 times 2? Is that it? No. Nothing's in there, so we're done. Okay? So we're going to take the square root of both sides. So B is equal to the square root of 38. So we're going to be in here. Okay? Can't break that down. Look at my list of perfect squares. There isn't one in there. So I'm finished with that. All right, that one's fairly straightforward. Okay, so that's the Pythagorean theorem in a nutshell. Good old Pythagoras and the rope stretchers. They actually formed a cult called the Pythagoreans, and where gods were all numbers, and I think they might be still around today. They might be associated with the Wiccans, which also idealize numbers with the tarot cards and all that kind of stuff. But he had quite the following for very many years. I mean, he was around in 500 BC, and they had been using this for a really long time. So we've been using this theorem. We've been using this mathematics for like 2,000 some years. It's amazing how much we knew way back when. All right, so now let's blow that up a bit. It says, what does it say? Find the length of the segment. Okay, we want to know how long this thing is. Well, that's pretty straightforward when we know the formula. So let's write down the formula, shall we? All right, we have the distance formula. Okay, so this is the distance between any 2 points on a line. The distance is equal to x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. So your distance is between this point and that point. Okay? So, you know, if I had a point, 1, 3, let's just make them up, and 5, 8, I could throw, like, x1 is 1, y1 is 3, x2 is 5, y2 is 8. I just throw them in, and I crunch the numbers. Okay? So look at the one we have here. We don't know what these are, right? But I can sure find out from my graph. So let's first of all write down what we think these points are. These are going by ones, right? 1, 2, 3, 4, 5, 6. So first of all, figure out your scale, because they, sometimes they go by 2, sometimes they go by 5s. So here we have negative 1, 2, negative 3, 2. Isn't that point? So we have negative 3, comma 2. That's going to be my first point, so that's going to be my x1, y1. The subscripts here just mean that it's my first point, kind of like when we were working with slope. This will be my second point, or it could have been vice versa, it doesn't matter. We've got 2, 1, 2, 3, 4, 5, 2, 5. So my second point, which is x sub 2, y sub 2, is 2, 5. Now I'm plugging it into this formula right here. So the distance between these 2 points is the square root. It tells me to take x2 minus x1, x2 minus x1, minus, be careful with your signs, right? I'm subtracting a negative, and I'm squaring that. Then it tells me to take y2 minus y1, so 5 minus 2, that's more straightforward, and squaring that. So do some work. What is 2 minus a negative 3? Isn't that like 2 plus 3? Certainly is. Subtracting a negative is like adding. All right. 2 plus 3 is 5. 5 minus 2 is 3. 5 squared is 25. 3 squared is 9. Square root of 24? Nope. 34, Simone. It didn't look right, and I couldn't figure out why. Square root of 34. All right, so at this point, way up in here, we could probably do it on the calculator. Let's try it. All right, multiple sets of parentheses. I've got 2 minus a negative 3, and I want to square that, and I want to add it to another set of parentheses, which is 5 minus 2, square that, and then I want to close my parenthesis from my open radical. So let's try the square root of 34. See if we get the same decimal. Oh, we do. So we've done it right. Square root of 34. This calculator won't give me the square root of 34. It's going to give me the decimal version, so I'm going to check that against it. Now I'm going to go back and I'm going to see, okay, can I reduce 34 at all? I'm looking through, again, I'm looking through these numbers. And 34 is not reducible. 4 doesn't, that's done. So we've got the square root of 34. Oops, I got to get rid of this first. Let me take square root of 34. Nice work. So this distance right here is about 6 long. Does that look about right? Yeah, it looks about right. Okay. I'm not going to do all of these. Look at your scale. Be careful. These are going by tens. So this point would be negative 10, 20. This point is 30, 30. And you're going to slap it all in there and simplify the radical if you can. So I'll do another one. Let me just see. Okay, let's try this one. This time we've just been given the points, not a graph. Not a problem. x1, y1, x2, y2. We're still plugging into that formula. Where is it? It's way up there. Okay, so we have d is equal to, all right, so we have x2 minus x1. And then we're going to add y2 minus y1. Careful. Okay. And we have 5 squared plus negative 1 minus a negative 8 is like negative 1 plus 8. This is 7. And then you would square 25 and 49. That's the square root of 25. I keep telling you I can't do math in my head. I can't add. 74. Don't laugh at me. What's in a 74? Oh boy, I have no idea. Is there a 16 in there? No. I think that's done. Let's go to 74. Let's just try it. I'm being really lazy. Do you guys do that too sometimes? Instead of really checking out the calculator on your homework, you go, well, it'll tell me if it's right or wrong if I need to keep working with it. I should not show you that. That's really bad. Same thing. Oh, this one says round to the nearest thousandth. So if you get an answer like this, it's going to want the actual decimal value. Okay, so at this point, let's just say this was my answer. I would go one step further and put in to the nearest thousandth 8.602. Okay, so be careful on the directions. Type your answers. Ooh, this one I have to do. Find x if the distance between the given points is d. Assume x is positive. All right. This one's a little different, isn't it? X -3, 49, 17, and we have the distance is equal to 52. All right, we better get that formula back out here, huh? Okay, so this is, what is it? X2 minus x1 squared plus y2 minus y1 squared. Okay, x1, y, that's a y, good lord, y1, x2, y2, and d. So I'm going to put in what I know. I know the distance is 52. X2 is 49 minus x. And y2 is 17 minus a -3. Okay? All right, what do we have here? What do we got going on? Well, here we have 49 minus x plus, what do we have here? We have 17 minus a -3. 17 minus a -3. It's like 17 plus 3, right? So it's 20. And then we'd have 52 is equal to 49 minus x quantity squared plus 400. Okay? So far so good. Where did my thing go? Sure hope I'm, yep, okay. All right. All right, so where do we go from here? Let's get this down a little bit. Well, it looks like a mess to me, but I see a radical sign, and I know how to get rid of a radical sign. I square, right? So if I took the square root of this entire thing on the inside, or the square, excuse me, and then squared this side, I think I'd be at least getting rid of my radical, because the square root of a square is itself. So let's see what 52 squared is. 52 squared is 2704. And the square root of a square is itself, so all I have left is this. Okay? So all I'm doing right now is I am trying to clean up my radical, and that's what we just learned in that previous 10.6, the first 22 problems, I think it was. All right, well, now I got to keep going here. I've got 2704. That's why I make sure to do this one. This one's a little trickier than most. I have, don't I? Well, I've got a FOIL. 49 times 49. What is that? 49 squared. 2401. That's my first term. My outside is a negative 49x. My inside is a negative 49x. And my last is 8x squared. Now what do I see? Immediately what comes to my mind is I've got a quadratic. I've got this. So I'm going to want to set it equal to 0, factor, and solve, because that's the only thing I know at this point. All right, these are alike terms, and these are like terms. So we're going to combine. We've got 2401 and 400 is 2801, right? Then I have negative 49, and negative 49 makes a negative 98. And my x squared. Now I'm going to subtract that across. Try to get my 0, right? I'm going to write this in descending order, because then it's going to look more like a regular trinomial. So I've got 2801, and I'm subtracting 2404, and I've got 397. Something went haywire there. 2401, what happened here? 2801 minus 2404. Well, why did that turn into a 4 when it was a 7 all along? I did it again! Oh good, I get my eraser back out. I like this eraser. See, you gotta play with this stuff. Get rid of that. Get rid of that, get rid of that. Get rid of that, and we should be good. Hate when I make mistakes. 2704, 27, 27, 2704. All right, so we have 2801 minus 2704 for 97. That looks way better. Positive 97. Okay, sorry about that. All right, so we have our quadratic. It boils down to this. Set equal to 0. Now I'm going to factor. I look at this as one of those easy trinomials. All right, what's my variable? Well, it's x. I have a positive, so they're both going to be the same, and they're both going to be negative. And I'm looking for factors of 97. The only one that I really care about is this, because they have to add to 98. I don't care if there's others. There could be. Although 97 seems like it could be prime too, doesn't it? I'm not sure if it is or not. Anyway, now I have something times something is equal to 0, so either x minus 1 is 0, or x minus 97 is 0. Adding my 1 across gives one answer. Adding my 97 across gives me my other answer. So either one of these should work. All right, now in a test situation, I would actually go back into this row right here. This one right here. I'm going to put a check mark by it. This one right here, and I'd check them. Let's just try the 1, okay? So I have the square root of 49. I better get another set of parentheses in there. 49 minus 1. I want to square that. And then I want to add 20 squared. Close my parenthesis. 52. There's my distance. So that one does work. If I put a 1 in here, I get the 52 back out. Now I will do the same thing for the 97 and check it. Okay? Let's check it this way since it is just a homework problem. Well done. All right. Good. Okay. What else do we have in here? We're almost done. And I think okay, so the back part of this is all word problems, which I know you guys just absolutely love, right? I'm going to get you started on some of these. I don't think I need to do all of them. They're pretty straightforward, and once you have the concept, I'm going to let you do the math. But think about your TV, okay? TV sets are usually rectangular in nature. This one says it's 10.8 by 14.4, okay, inches. Pretty small TV. And we want to find the diagonal. That means what is the length of that? Well, you can see that this is a 90 degree here, and if you pull that off to the side, it forms a nice right triangle, and you're missing the hypotenuse. You know how to do that. A squared plus b squared equals c squared. All right? Let's look at what this one says. When skydivers initially fall from an airplane, their velocity in miles an hour after free falling so many feet can be approximated by this formula. Because of air resistance, they will eventually reach terminal velocity. That means that you can't get any faster at some point. That does not mean you're dead, terminal. How far do skydivers need to fall to attain a velocity of 30 miles an hour? Okay, well, remember, what have I always, well, I think I need a new screen. I do. What have I always told you about word problems? Especially when you have a function type word problem. Well, I hope that you remember that you have to label what you have. What are your sides? Okay, so let's get our formula written down first. V is equal to 60 over 11 times the square root of d. Input, output. What is my input? What is d? This is how many feet you've fallen. Feet fallen. What is v? Velocity. Speed. If you ever take physics, you'll know that speed and velocity are basically the same thing. One's got a direction attached to it. That's the velocity. That's a vector, if you've ever taken any kind of physics. But you can think of it for right now, because we're not in a physics class. You can just think of it as speed. Okay, so your speed is dependent on how many feet you've fallen. Okay, so when you first get out of the airplane, when you first fall out of the airplane, you're not traveling very fast, and you're going to build up your speed. Okay, so this one says how far do you need to fall? So we're looking for d to get all the way up to 30 miles an hour. So when it says this, you know where to put the 30. The 30 does not go here, it goes over here, because you've been given a speed. So once you label these things, it's pretty easy to figure out where things go. All right. Now, we have to solve for d, so I'm going to get rid of this 60/11ths by multiplying by the reciprocal. Look what happens when I multiply by the reciprocal. 60 is gone, 11s are gone. So if I do that on this side, I have to do it on this side. So this is gone, and this is gone. So now I have 11 times 30 over 60 is equal to the square root of d. Let's see if that's a nice number or not a nice number. Divided by 60. It is a sort of nice number. Okay, so we want to round. Okay, so we'll say that's 5.5. It's not looking for an exact answer. All right, so how do I get rid of my square root? Square both sides. 5.5 squared gives 30.25. So that's my distance. 30.25 is equal to d. So what this is telling me is if I want to hit 30 miles an hour, it's about 30 feet down, right? Is this 30? Excellent. This piece of it right here is pretty important as well. When it tells you not to round until the very final answer, that means if you have all these intermediate answers, okay, and let's say they're all decimaled, drag them out as far as you can until the very end and then round. Okay, that's terribly important because you can get the wrong answer if you don't do that. Okay, so if you have a bunch of answers that are coming down and they're all full of decimals and all that, drag out your decimals to the very last one. Okay, sorry, I had to take a sip of pop. All right. Draw a picture. We have a pole. We have the ground. And we have a guy wire. Right? The pole we're going to assume is straight, so that makes a 90-degree angle with the ground. Okay, so how long is a guy wire? How long is that thing? Reaching from the top of a 24-foot pole, so this is 24 foot to the top, to a point on the ground that's 16 feet from the pole. Well, that's here. Again, we can pull that off to the side. Forms a super nice right triangle with a missing hypotenuse. You know how to do that. Type an exact answer using your radicals. Okay? Piece of cake. I think you've got a formula in here. Yeah, you've got a formula in here. The only thing that I want, I'm gonna let you find V if V is this, D is this, and D is that. So you're just plugging stuff in and you're solving. Now you have a V and a V and a D and a D. Okay, capitals and small case are not the same. All right, just so you know, sometimes they're related, but this capital V is what you're looking for, and this small v is 45. The capital D is 315, and the small d is 180. Okay, and again, don't round until you come to the final answer. So they just want you to plug it all in. Well, I suppose that's too easy. That's too easy. It's all on one side, so. And then there's another part. It's probably looking for one of these three pieces when you know that. So that's just solving the other way. And I think I really do. I think these are pretty self-explanatory. Label, input, output. What is your V? This is your velocity. What is your W? It's your wattage. Okay, so a generator depends on the wind of the wind of the speed, right? The speed of the wind is determining how much wattage it generates. Okay, and I'll do this one. All right, what kind of a triangle is that? Anybody want to go back into the very beginning of my lecture on types of triangles? It's an isosceles. What did I say an isosceles was? An isosceles has these two angles the same. When you put a tick mark through it, that means these are the same. And then it's got the two base sides that are the same. That's what this is. We've got the two angles are the same, and then the two sides are the same. It's just been flipped. And in our case, this happens to be a 90. So it happens to also have a right triangle. So there's only in one case, there is a isosceles, which is a right triangle, and that's when both of these other angles are 45s. Otherwise, they're not. Then this is not a 90. So this is one of those special cases where it happens to be a right triangle and an isosceles triangle. Okay? We want to find the length of the hypotenuse. Well, that's pretty simple, isn't it? We're going to use our a squared plus b squared equals c squared. I can because of the 90. I'm going to just call this a, b, and c. Okay, and I'm looking for c. So I'm going to plug in what I know. I know a is z. I know b is z. And I'm looking for c. Okay, I'm solving for c. I've got a z squared and a z squared for two z squareds. Now I'm going to get rid of my square on my c because that's what I'm solving for. So I'm going to take the square root and the square root. Square root of a square is itself. And now I have 2z squared. This is multiplication, so I can split it. Square root of 2 square root of z squared equals c. Square root of 2 is not perfect, and you can't get anywhere with that, so we're going to leave that one alone. So we're going to do radical 2. But the square root of a square is itself, so the z can come out on the outside. So there's my side. Square root of 2 times z is c. I know that looks like a goofy answer, but that's what it is. I don't think it really matters when on the order there, or z times the square root of 2. Okay, just be careful, don't put your z underneath the radical sign, because as you can see, it came out. So that's why we usually put those first and then the radical sign, because sometimes it's hard to see if it's underneath there or not. Okay, but in any case, that's it. That's 10.6. That's a lot of work. That's why we wanted to split this one in two and take out 10.5, because otherwise it just won't work. So one more section, 10.7. There's going to be 30 problems in that one. I think we can handle that in one shot. And then you'll test on just these two sections. So good luck.